Welcome to the first lecture of VLSI, which is the second unit for UGC Net Electronic Science paper. The topics covered in this lecture are as follows. We will start by seeing the basics of IC, what an IC is. Then we will move on to the methods involved in the fabrication of an IC, followed by the advantages and disadvantages of using ICs. The next topic will be the commonly used IC terms. We will then conclude the lecture by studying the steps which are involved in the fabrication of ICs. So let's get into the video. The term IC stands for integrated circuit. An IC, also called a chip, is a semiconductor wafer on which thousands of tiny resistors, capacitors, diodes, and transistors are fabricated. It is a building block of all modern electronic devices. There are different types of IC fabrication techniques. So, the first one is monolithic IC technology or epitaxial IC technology. The word epi means single. In this method, entire IC is fabricated on a single crystal of IC material. This technology is used for fabrication of active components such as BJT, JFET, MOSFET, op-amp, diodes. Monolithic technology is exceptionally used to fabricate resistors, which is a passive element. The next two technologies are thin film technology and thick film technology. Both the above methods are used to fabricate passive components mainly and can be extended to active components as well. Now, let us study what are the advantages of IC fabrication. First, reduced cost. Second, miniaturization. Third, portable. Next, ICs are highly reliable with minimum electrical and mechanical failures. Improved performance when compared to discrete circuit performance. Next, very lightweight, ease of replacement, and low power consumption. Now, let us see what are the disadvantages of using ICs. First, ICs are sensitive to humidity, high temperatures, and voltage fluctuations. Second, ICs can handle only limited amount of powers. Next, ICs cannot handle rough handling as they are very delicate. Next, they cannot be used to fabricate coils and inductors. Now, let us see what are the generations of ICs. So, the first one is SSI, which stands for small scale integration. Here, the number of transistors used are 1 to 10. Next is MSI, which stands for medium scale integration, and the number of transistors used for this technology is 10 to 500 transistors. Next, we have large scale integration, also called as LSI, where the number of transistors range from 500 to 20,000. And next is VLSI, which stands for very large scale integration, and here number of transistors are anywhere between 20,000 to 10 lakh. Next we have ULSI, which stands for ultra large scale integration, in which the number of transistors are greater than 10 lakh. So next let us have a look at what are the commonly used IC terms. The first one is wafer. A wafer is nothing but a thin disk of semiconductor in which number of ICs are fabricated simultaneously. Next, chip. A chip is an extremely small part of silicon wafer on which IC is fabricated. Next, circuit probing. Circuit probing basically refers to testing the electrical properties of each IC with the help of a microscope and multi-point probe. Next we have is die, which is a same as chip. Next, diffusion, a process that consists of the introduction of impurities into selected regions of a wafer to form junctions. Next, encapsulation, which is putting a cap over the IC and sealing it in an inert atmosphere. Next, epitaxy, a process of controlled growth of a crystalline doped layer of silicon on a single crystal substrate. Next, etching, a process of selective removal of regions of a semiconductor metal or silicon dioxide. Next, mask. A mask is a glass plate with desired pattern for diffusion or metallization. Usually, a single mask is not sufficient to fabricate an IC. The next term is metallization, which is a process for providing ohmic contacts and interconnections by evaporating aluminum over the chip. Next, photolithography. Photolithography is a process to transfer geometrical patterns from the mask to the surface of the wafer. Next we have is photoresist, which is a light sensitive material that hardens when exposed to UV light. Next, bonding. Bonding, which stands for attaching the die on the ceramic substrate and then connecting the leads to the package. Now, let us have a look at what are the steps involved in the fabrication of an IC. So, these are the following steps. First one is crystal growth and preparation of silicon wafer. Next, epitaxial deposition. Third, oxidation, followed by photolithography and chemical etching. Next, diffusion, followed by ion implantation, metallization, and circuit testing. So now we will have a look at each one of these steps in greater detail. First, crystal growth and preparation of silicon wafer. This is generally the first step in IC fabrication. The starting material is highly purified polycrystalline silicon, which is composed of many small crystals having random orientation and containing many defects. For silicon to be used in the fabrication of ICs, it must be perfect and crystalline in nature. Thus, we need to provide single crystals of silicon. This is done by a process called crystal growth. Crystal growth can be done by two methods, which are Joukhalski process and the flat zone process. Here is a diagram for both the methods. Next, the Joukhalski method. This process is the most often used for producing single crystal silicon ingots. The polycrystalline silicon together with an appropriate amount of dopant is put in a quartz crucible and is then placed in a furnace. The material is then heated to a temperature in excess of the silicon melting point of 1420 degrees Celsius. A small single crystal rod of silicon called a seed crystal is then dipped into the silicon melt and slowly pulled out. A precisely controlled amount of dopant, which is boron or phosphorus, is added to the melt to make the silicon as p-type or n-type. Usually using this method, cylindrical single crystal bars called ingots of silicon are produced. The resulting ingot is cooled and is removed to be made into thin discs called wafers. Next, we move on to wafer preparation. Here, ingot is marked with two flat regions. First is the primary flat, which is also called as the larger flat. It allows a mechanical locator in automatic processing equipment to position the wafer and to orient the devices relative to the crystal in a specific manner. Second is secondary flat or smaller flat. These are used to identify the orientation and conductivity type of the crystal. The conductivity of the wafer could be either p-type or n-type. Now, next step is wafer fabrication. The following processes are used for wafer fabrication. First, oxidation, next etching, then diffusion, followed by ion implantation, photolithography, epitaxy, metallization and interconnections. Let us have a look at each one of these. Oxidation. The silicon wafer manufactured in is not yet conductive. It has to go through a process to make the wafers semiconductive. First, wafers grow through the oxidation process. Oxygen or water vapor is sprayed on the wafer surface to make a uniform oxide film. This oxide film protects the wafer surface during the subsequent processes and also blocks current leakage between circuits. The film acts as a strong protective shield. There are basically two types of oxidation processes. First is dry process and second one is a wet process. Next, etching. Etching is used to remove unnecessary materials from the wafer surface so that only the design pattern remains. This is done using a liquid or gas etching technique. All necessary materials are selectively removed to draw the desired design. Two types of etching methods are generally used. First one is wet etching. When the chemical solutions are used for etching, it is called as a wet etching. Second, dry etching. When gas or plasma is used, it is called as dry etching. So this is the process which shows vapor etching process. Here, isotropic, which means etches equally in all direction, and the second term is anisotropic, which means etches at different rates in different directions. Moving on to the next step, which is diffusion. So, this process consists of introduction of impurities into selected regions of a wafer to form junctions. Diffusion can occur in two steps. First is pre-deposition, which tends to produce a shallow but heavily doped layer near the silicon surface. Second one is drive-in diffusion. It is used to drive the impurity atoms deeper into the surface without adding any impurities. More recently, a more accurate method of pre-deposition known as ion implantation is used. Now, we will study what is ion implantation in detail. Coating the thin film at a desired molecular or atomic level onto a wafer is called deposition. Since the coating is so thin, precise and sophisticated technology is required to uniformly apply the thin film on a wafer to give the semiconductor electrical characteristics. Ion implantation. Ion implantation is also required. A semiconductor made of silicon does not conduct electricity but adding impurities. It conducts current and has conductive properties. So you can clearly see in the diagram the process of silicon ion implantation. The red marked region is the doped region. Next we have is photolithography, which is usually the next step to draw a circuit design onto a wafer, which is called the photolithography process. It is also called photo for short because it is similar to developing a photo taken on a film camera with semiconductors. A photo mask functions as the film. A photo mask is a glass substrate with a computer designed circuit pattern. In order to draw the circuit on the wafer, the photoresist, a material that responds to light, is applied thinly and evenly on the oxide film previously placed on the wafer. Now, when light transfers the patterned photo mask, the circuit is drawn on the wafer surface. Just like developing a photo, a circuit pattern is imprinted on the wafer by spraying developer and removing unlit areas from the areas that are exposed to light. After an inspection of the wafer to check whether the pattern is drawn well, it moves on to the next step. The next step is epitaxy. It is the process of controlled growth of a crystalline doped layer of silicon on a single crystal substrate. It is used to produce a layer at the surface of lower concentration. To form epitaxial growth, various methods include vapor phase epitaxy, liquid phase epitaxy, and molecular beam epitaxy. Next we have is metallization and interconnection. Now, in order for the circuit to work, an electrical signal must be applied. So, it is necessary to create a path for electricity to pass through according to the circuit pattern. This process is called the metallization and interconnection process. It is a process that allows electricity to flow by depositing a thin metal film using materials such as aluminum, titanium, or tungsten so that electricity can pass through the semiconductor wells. After all the steps are done, the last and the foremost step is testing, bonding, and packaging. Now, what is testing? So, after the wafer has been processed and the final metallization pattern defined, it is placed in a holder under a microscope and is aligned for testing by a machine called multi-point probe. The probe contacts the various pads on an individual circuit, and a series of tests are made to verify the electrical properties of the device in a short time. Next is bonding. It consists of two steps. In the first step, the back of the die is mechanically attached to an appropriate mount medium such as ceramic substrate, multi-layer ceramic package or metal lead frame. In the second method, the bond pads on the circuit side of the die are connected by wire to the package. Next, packaging. This is the last process. The packaging process. The wafer completed through the previous steps are cut into individual semiconductor chips that can be loaded on an electronic semiconductor device. An individual chip must have a path to exchange electrical signals with the outside and have a form to protect it from various external elements. The wafer is cut into individual chips and the diced or saw chips are placed on the PCB board. In the bonding step, the contact point of the semiconductor chip placed on a substrate is connected with the contact point of the substrate. Then molding finishes the chip package to its desired shape. After the final test, sealing and labeling the product name, the semiconductor chip we commonly see is completed. So this was all for today's lecture. Thank you. Please do not forget to like, share and subscribe to my channel so that you do not miss any future uploads.